So today class is about the lab number 7, and lab number 7 we will design a Yagi antenna, and this antenna is also called Yagi-Uda antenna because it was firstly designed by these two peoples. And you know that what is antenna, we have discussed this in previous classes. In the previous two classes, we also discussed the dipole antenna. In today's class, we will study the Yagi antenna. And the shape of the Yagi antenna is like this. And you may have seen this antenna. This is the Yagi antenna. This is the reflect. I will share the whiteboard. The title is title of the lab is design Yagi antenna in CST studio. First of all, I will discuss some basics about the Yagi antenna. The Yagi antenna is a directional antenna. What is meant by directional? For example, you know that there are some antennas. If, for example, if this is an antenna and they radiate the power in all direction, then this is called omnidirectional antenna. Omnidirectional antenna is that antenna which radiate the power in all possible direction. While the directional antenna will radiate the power in specific direction. For example, in previous class you studied the dipole antenna. This is the dipole antenna. In the dipole antenna will radiate the power in uh, two direction. This and this. You have studied in previous class that the dipole antenna will radiate the power in two directional, here and here, at 0 and 180. It means that the bidirectional antenna are those antenna which radiate the power in a specific direction, and all the antennas in practically they are directional antenna. They radiate the power in a specific direction. That is why in BTS and base station for wireless communication, if this is a base station, in base station we use three antennas, And you may know from your wireless communication, either you will study in your final term that we will design the we will convert the whole area in cells. This is the cell structure. Sorry, this is the cell structure. Hexagonal shape. Sorry, this is okay. This is the hexagonal shape. And if you divide this, so they cover the 120 degree. So we will use the one directional antenna in this region, in one direction antenna in this region, one direction antenna in this region. So therefore, simple, I say that the Yagi antenna is directional antenna, so it will radiate the power in a specific direction. How it will radiate, it will be covered soon. The maximum operation of the antenna is above 10 megahertz. About 10 megahertz. It will operate in about 10 megahertz. And it can be used for sending the signal from 40 to 80 kilometer. It covers this range that we will receive the signal from 40 to 80 kilometer. There are two types of element in the Yagi antenna. There are two types of elements in Yagi antenna. One is two types of element. The one is active element, active elements, and this active element is called driven. And this driven will be dipole antenna. Dipole antenna. And the second is called parasitic elements. These are reflector, slash, and director. What is mean by active element? Active element are those elements which are energized by the external source, and they will radiate the energy. They will radiate the electromagnetic waves. The parasitic element are those elements they are not energized by a source, and these are used for directivity and for suppressing the unidirectional uh, radiation. For example, it will be clear in the structure point of view. Now I want to show the structure, and then it will be clear that what is the effect of the active and what is the effect of the parasitic elements in Yagi antenna. So the structure of the Yagi antenna contains three elements. One is reflector, one is driven and other is director, and these are basically two elements. One is active and one is parasitic. The This is the reflector parasitic element. This is the reflector, and this is the dipole antenna, and which is energized by some force, some AC source. And then there are director, and sometimes there are sometimes there are more than one directors in antennas. For example, here, and you may see this antenna in your home or TV. And this antenna you may see the one, the first uh, the first wire is large, then the second is smaller than the first, and then they become smaller and smaller. Hope you know this antenna. This antenna is called Yagi antenna. And this Yagi antenna, this is the reflector, and this is the main component which radiate or accept the radiation. This is the dipole antenna, and all others are director. So what is the function of reflector and what is the function of dielector? So the function of the dipole or the driven is that it will radiate the energy and it will receive the energy. But what is the energy effect of these two other elements? So consider if there is only one dipole antenna, there is only one dipole antenna, so you know they radiate the energy in such a form. Such a form. If we place reflector, so what is the function of reflector? It will reflect the energy. This is the reflector, and this is the dipole antenna are driven of dipole. So then this radiation will be reflected back by this reflector. This is the reflector, and this is the driven. So when they will reflect and this, so they will produce two minor loop and other major loop. This is the major, minor loop and major. And this minor loop is due to the reflector. Is the reflector will reflect this radiated power in this direction. So from this, the power radiated by dipole in this direction will be converted into forward direction. So it will increase the directivity, and also it will minimize this power. When we insert the director, when we insert the director, and the size of the director will be smaller than this. This is the driven, this is the director, this is the reflector. Then there will be some minor loops, and this director will also convert this beam into narrow beam, and that is why the directivity will be large. And you know what is directivity? If this loop is narrow, it means this is very strongly directional. By directional, we mean that it will cover to a specific point. So you know that there is the 3 dB bandwidth is large. The 3 dB bandwidth of this is large, and the 3 dB bandwidth is very small, very sharp. So mean this is a strongly director. It has very high directivity, and you may know, and you can see this in your this is the radiation pattern of Yagi antenna. There is some minor loops, and there will be some, and this is a major loop. This director will direct the radiation in a specific direction. So there are three components in the Yagi antenna. One is the reflector. The function of the reflector is to reflect the power in forward direction. The driven, this is a dipole antenna, and this is a dipole antenna, and it will radiate the power. And the third one is director. Director are directors. If there is a one element, so this is a director. If there are more than one element, so then there are directors. So these directors will direct the radiation pattern in a specific direction. So for this, the directivity of the antenna will be increased. Here in this lab, we will design the Yagi antenna, which contain just three elements: one reflector, one driven, and one director. So the shape will be like this. This is the reflector, this is the driven, and this is the director. And you see the size of the reflector is greater than the size of the driven, and the size of the driven is larger than the size of the director. This is driven, this is reflector. So how you will design the size, how you will select the size of reflector, the size of driven, and the size of director. For example, in dipole point of view, we will design, we will find the lambda of specific frequency, then we will design a dipole antenna which is lambda by 2, smaller than lambda by 2. But here, there are LR mean the size of reflector, the length of reflector. The length of reflector will be given by equation 492 by frequency, and you make it is you may note it that the frequency will be in megahertz. The frequency will be in megahertz, and when we divide this, we will get the answer in feet. Then you can convert this into centimeter or in millimeter. But when we apply this formula, so the answer will be in feet. Then we will convert this feet into centimeter, either millimeter. For LA mean, L of eq2 element and eq2 element is driven. So LA is 4 78 divided by f, and it is noted that this frequency must be in megahertz, and the answer you will get in feet. The length of the driven will be calculated by 461.2 divided by frequency, and this frequency will be in megahertz, and the answer will be in feet. Now what is the spacing between them? What is the value of the spacing? So the space will be 0.25 of the lambda. You will calculate the lambda. For example, if you want to design a Yagi antenna for 1 gigahertz, so we will calculate the lambda, and then 0.25 multiplied by lambda will be the space between the elements. Elements mean by distance between the reflector and driven, and the distance between the driven and the director will be 0.25 lambda. 0.25 lambda. This is the theory behind the Yagi antenna. The advantages of the Yagi antenna is that it is a high gain antenna, and its gain is about 9 dB, and it can be it can be increased up to 20 dB, and it has the high front and back ratio. High front and back ratio means that it can radiate the energy only in forward direction. It is cheap, you can design easily, and it is light in weight. The weight of the antenna is light. Please mute. Uh, and the disadvantages is that the size of the antenna is very large, and the second limitation is that we can't uh, improve the gain beyond the 20 dB. It can be used for home TV receiver and also for point-to-point communication. If you want to communication from just one point to another point, point-to-point communication, this is the application of the Yagi antenna for point-to-point application, and for home TV receiver, you can use this antenna. So let's design an antenna for 1 gigahertz. This is our task. Design a Yagi. Sometimes we say that design a Yagi antenna, and sometimes we say that design a Yagi-Uda antenna. Why Yagi-Uda? Yagi and Uda are the two scientists. They designed this antenna. So the Yagi-Uda antenna for 1 gigahertz. 1 gigahertz. So first of all, when you design this, so you will convert the frequency into mega, because we have write the formula which is only applicable in mega. So you may know 1 gigahertz is equal to 1000 megahertz. 1000 megahertz. So we can calculate the three value. LR is equal to 492 divided by 1000, and this is equal to 0.492 feet, and this is approximately is equal to 15 centimeter. You can convert by using the Google converter that convert the feet into centimeter. Second, LA mean length of dipole or length of active element. So this is equal to 478 divided by 1000, and this is equal to 0.478 feet, and this is approximately is equal to what? It is equal to 13.8 centimeter, either 14 centimeter. And you can calculate the length of director. This is equal to 461.2 divided by 1000, and this is equal to 0.4612 feet, and this is approximately equal to 12 centimeter. And when you calculate the spacing space between the two elements, so it is approximately 6 centimeter, and you can calculate by this equation. Try yourself that lambda c is equal to f lambda, and the lambda will be equal to, or here I can write this, that lambda is equal to c by f. Calculate the lambda, and then write the space is equal to 0.25 multiplied by lambda. You will get some value. When you convert this into centimeters, so it will be approximately 6 centimeter. So when we design the antenna, so we will design LR, we will design LA, we will design LD. This will be 15 centimeter, this will be 13.8 centimeter, this will be 12 centimeter, and the space between the element will be 6 centimeter. So let's move toward the designing. For designing point of view, I will design the Yagi antenna in CST Studio. Here you can create the new project. We will design antenna, and this is also a wire antenna, so we will select the wire. Next, and this is in time domain. Next, you may know this is in millimeters, so you will convert this into centimeter. This is in gigahertz. You can, as we have already convert the 1 giga into mega, so this is 1000 mega. Here you can use the giga, no problem. And we design the antenna for 1 gigahertz, so we will select from 0 to 2 gigahertz. So the when we study its far field, so we will only study for one value. One value means the center value, so 0 and 1. So when we want to design the antenna for 1 gigahertz, so it will give the value for the 1. Next, write the name Yagi antenna class and finish. So, for modeling point of view, I will select cylindrical. A cylinder as the wire is cylindrical form. This is the reflector, and its radius is very minimum 0.1. Its center is 0, 0, and its length will be minus 7.5 to 7.5. So from 7.5 to 7.5, the value will become 15. And you can calculate, you can design this from PC. As we have studied it, for antennas we will use two material, either PC, either copper. So if we preview, this is the reflector, and you may know this is the center. So I will design the, this is the reflector, so I will design at distance of 6 centimeter. Here we will design the active element dipole antenna, and at some distance here. So take the cylinder. This is the active element or dipole. The antenna in Yagi antenna is dipole. The dipole is the main component of Yagi antenna. Its radius is 0.1. Its center is 60. What is mean by 60? We have for reflector we select the center is 0, 0. Then we select the 60 mean some apart here 6, and so it will we have give a space of 6 centimeter in this here. ये तो space हो गया. Now when I want to apply the size, so for size point of view it is if we take from minus 6.9 to 6.9, so this will be 13.8, and this is also we will calculate design from PC. So this is the preview, and this is okay. This is the second component. Now we will design the director. This is the director. It is 0.1. It will be 12 from. So if we move 12 from the reflector, so it means 6 from the director. And this is 12, so minus 6 to 6. And this is also from PC preview, and okay. This is the Yagi antenna. This is the reflector. This is the dipole, and this is the delta. But you know that in dipole we were add the gap between them. So for gap point of view, we will generate another cylinder here and then cut it. So here I want to show you a second way that how you will produce the gap in this. So for this you will click on dipole. So you see when we click on the dipole is selected. Right, right click on dipole and go to transform and copy and scale. Then the scale is not uniform, as we want to very minimum gap. So for minimum gap we will 1.2 or 20. 120 be a small portion you see here, and if this is you click this less, so if you click this is more. So the material we want to change, so this is a space with you. When we design a cylinder of vacuum, it means that we have design a gap between the dipole, because uh, you know what is vacuum. In vacuum there is a no material, and if you preview it, you see here this is the cylinder in a gap form. Okay, so you will insert the highlighted shape. So when we insert the highlighted shape, it means that we insert the vacuum uh, vacuum type cylinder here, and this is the dipole one. So rename it by gap. This is the gap. If you select dipole and you see this is the gap, the cut has been produced between the dipole, the center of dipole. Now I want to apply. Now I want to apply. What are you asking, Suleiman? Hello. So if you want to design, uh, if you want to apply the alternating current here, so for this we will use the port, and for port point of view, you know, we will apply the discrete port here. This is the discrete port, and go to simulation and apply the discrete port. Okay. Clear? Any question? Can I proceed further? let's proceed. So this is the all about designing that we design the dipole antenna. Now we want to simulate the antenna. So we will go to here. You can increase accuracy up to 50, and if you want to accuracy up to 30, so this is okay, no problem. And simulation, it will take some time, and after the simulation we will see that the S parameter, that is it resonate at 1 gigahertz or not, and then we will check the directivity and the radiation pattern, that is the reflector has process or not. For example, if this is only dipole antenna, so then the radiation pattern was that. And now we have applied reflector and director, so its shape will be like this. So after simulation we will check that is our radiation pattern is okay or not, and is this is resonated at 1 gigahertz or not. I will stop the recording for some time.
The paper washing, guys.
So let's see, the simulation has been done. So if we check the 1D results, in 1D results this is S parameter. If we see the S parameters, so you see it is approximately 1. If you want to exact one, so you will change some lengths, and you can do this due to sweep parameters. So this is 0.956 gigahertz, so it means it is exactly 1. Uh, this is the S parameters of Yagi antenna. But if we check the far field graph, if we check the far field graph, and do let's transparent, show structure, you see the structure inside uh, the diaphragm, and it shows that it radiates the power only in this direction, and the second radiation and this due to the dipole has been suppressed by the reflector. This is the directivity 7.84, it is the directivity, so it has very high directivity. If you do the polar, Cartesian, 3D. So but you see the radiation in 3D is more visible. So this is all about Yagi antenna. In today class, we discussed that what is the Yagi antenna and how the Yagi antenna can be designed, and then we done our simulation in CST Studio software. Thank you.